I'm going to show you how to solve an exercise from this book. The book's name is Signals and Systems, the second edition. The authors are Alan Oppenheim and Alan Wilsky, with collaboration with Hamid Nawad. The publisher is Prentice Hall International. The problem that I'm going to talk about is from Chapter 2, Exercise number 22. And it goes as follows. For each of the following pairs of waveforms, use the convolution integral to find the response y of t of the linear time invariant system with impulse response h of t to the input x of t, and then we sketch the results. So the information we're giving is this. So we got the input signal x of t equals exponential to the minus alpha t times the unit step. And then we got the impulse response signal h of t equals exponential minus beta times t times unit step. Now we have to apply this convolution integral for both cases that are given here, when alpha and beta are not equal and when alpha and beta are equal. Now, as it mentioned before, the convolution integral is the relation between two continuous time signals, the input in this case and the input response, as is shown below. The convolution y of t is the output signal. So the convolution between the input signal and the impulse response signal is going to be the integral between minus infinite and positive infinite of the convolution of the input signals with respect to tau. Previously it was with respect to t, time. And the other one is the impulse response signal with respect to tau, with respect to t shifted a t value. Or in this case, we can say it the other way around. H of tau shifted or displaced by a t amount time. Now, before we actually apply this integral, we have to understand what are the limits or intervals that we have to consider. So for this, I have graphed the functions shown above here. You can see both of them are exponentials. The power that they got is negative, so they're going to be reflected. So they're going to behave the other way around. So you can see the graphs for the input signal x of t and the impulse response signal h of t are both decreasing exponential graphs with respect to t. Now, we have to consider the change of variable, in this case is tau, x of tau, and h of t minus tau. This is to be able to integrate better. Now, practically speaking, during calculations, we just have to substitute these values here for each type of signal. We replace tau on x by t, and then h we replace by t minus tau. So when we graph that, both signals, input and response signal, with respect to tau, we get this. We can see that we're converting tau with t minus tau, we get the displacement here. Now these are the two signals. Now that we have these two signals, I'm going to show you the following graph. What happens when we apply the convolution between these two signals? It means when we want to know about the output signal of the convolution between these two signals. For two cases, when time is less than 0 and when time is more or equal to 0. The first part, it shows when the convolution of these two signals when the time is less than 0. You can see h of t here when time is minus 0, and the other one, the input signal x of tau, x of t when it is less than 0, when t is less than 0. Now, what happens when time is more than 0? There is a shift, there is a displacement, and there is something happening here in between. This is called the overlapping. So when time is positive, is more than 0, it becomes there is an overlap. Now, overlapping, it can be considered like the crossing between these two signals. It's kind of like superimposing each other when both signals are occurring at the same time, but superimposing refers to superposition, which is a topic which is slightly different than what we need right now. Something very important to consider is that when time is less than 0, there is no overlapping. They are like separately behaving. Now, when time is more than 0, it goes positive, there is this overlapping here. When it goes from 0 to time t. Now, This condition here, the overlapping, is what we are going to consider in order to solve this question that they're asking us to do. So the limits, that the boundaries that we're going to consider is the interval for the overlapping interval between 0 and t. Now let's proceed with the calculations. Now, as I mentioned before, from the figures above, if t is more or equal to 0, there will be an overlapping of the signals, which is the part that is being highlighted here, shaded here. Now, when the overlapping limits of integration are going to be tau from equals to 0 and tau equals to t. Now, let's start the calculations when alpha and beta are not equal. So the desired convolution, by applying the relation shown before, is this one here. Now, the first step is just going to replace each signal that we're given. So x of tau is going to be e to the minus alpha tau, and h of t minus tau is going to be e minus beta times t minus tau, all with respect with minus tau, d tau. So this interval is going to be with respect to tau. Now, the intervals, as I mentioned before, are going to be between 0 and t because of the overlap. As you can see, that happens when t is more than 0. Now, the next step, as you may know, these are two exponentials that are equal. So the base are equal, but exponentials can be simply calculated by changing them. So the same base, different exponential, we just apply calculations to the exponential. So the first thing we're going to do is just rearrange this, remove the parentheses here, and then we're going to apply some common factor for tau. Keep in mind that for this integral, tau is going to be a variable of integration. Everything else are just constant. Now, we're applying for the exponentials a common factor alpha minus beta, and then we separate the other constants that are, in this case, just minus beta t. Like I mentioned before, this integral is just with respect to tau, so we can just take out the constant part. Now, if we integrate the part inside, we know that the integral of an exponential is the same exponential with the derivative, in this case, the inverse derivative of the antiderivative of the exponential. In this case, it's going to be 1 minus alpha minus beta, as it is shown here. So now that we have integrated the equation given, now we're going to apply the limits for each when tau equals to 0 and when tau equals to t. We know when we apply we replace t for tau, where t for tau here is going to be the same, except that the place here is going to be t. Now, there's a small mistake here, by the way, it should be t. When we know that we replace 0, 0 is going to become just 1, because any value to the power of 0 is just going to be 1. So the result we're given is this one here. Now, something we have to now apply is the unit step. Right? With a unit step, we can make sure that the signal is going to be for a time more or equal to 0. That means that because of the unit step, for t less than 0, when we apply the unit step here, when time is less than 0, the whole unit step will become 0. Right? So in other words, by using the unit step, we only consider the positive values. So that's why it is being used above here in the given initial equations, because it's asking for t equals more or equal to 0. But I wanted to make a reference what happens when t is less than 0. There is no overlapping here. So we use the unit step here. Now let's proceed when alpha and beta are the same. The same process, we apply the convolution integral with the same limits when t is more or equal to 0 because of the overlap. Now we substitute each of the equations that we were given before. Now instead of beta here, we just put alpha. So we are going to solve this in steps of alpha. We're replacing every beta with alpha here. Well, now apply the same exponential calculations. Then we apply a common factor. Then we see in this part here, in this part in particular, that alpha minus alpha is going to be 0. 0 times tau is just 0. And like I mentioned before, any value to the power of 0 is going to become 1. Now also, keep in mind that this part here is also a constant part. These are all constant values because this integral is being integrated with respect of tau. So we integrate that. In this case, it's just going to be 1. The integral of 1 with respect to any variable is just going to be the variable itself. In this case, it's tau. Now we solve the intervals when tau is equals to 0 and tau equals to t, and we get this value here. T times e to the minus alpha t. Of course, that happens when t is more than or equal to 0. Now, like I mentioned in the part before, we are going to we're going to add the unit step. This is so that we only consider the positive values. Now, following that, I just put a summary here of what the outputs are, the values here. As you can see, the t is here. I made a mistake here. I put tau, but it should be t. Now, these are the two results when alpha and beta are not equal and alpha and beta are equal. So as the question was asking before, I plot this using MATLAB, the output signal y of t for the convolution between these two signals, the input signal and the impulse response signal. As you can see the behavior of each graph, the red one is the second one, the first one we did is the blue one. So there is the main difference here is the amplitude when alpha and beta are the same. But like I mentioned, it was shown before the overlapping occurs from 0 to t. So let's see in the plot below. When time is 0, they're overlapping already. You see? Now when time, this is of course the graph with respect to t. Then we go towards the right hand side for the t, for all the values of t, you see that overlapping is still occurring. It goes all the way here, then it starts converging, but it is still overlapping with the two signals. So the two output signals are overlapping when t is more or equal to 0. That concludes the solution. Thank you very much.